So earlier we mentioned that if you had an alcohol with the Grignard, if you try to make the Grignard here, this reaction is not going to work. Because they will react with each other. So this is not going to happen. What you can do is protect your alcohol with a protecting group. So it's kind of like putting a little bodyguard on the alcohol so that the Grignard can't see it. So once you've protected the alcohol, you can add your magnesium, do the Grignard reaction. Your alcohol protecting group is still on here. Then you can deprotect it. And then you've done your Grignard reaction. And you have the alcohol back. It's a three-step process that's required to achieve the overall desired synthesis. So if we just try to do the Grignard reaction with the alcohol there, this won't work because this can get deprotonated and that reaction won't occur. But if you protect the alcohol first, that makes the Grignard not be able to see that there's an alcohol there. You do the reaction and then take the protecting group off and you get your alcohol there with your desired compound. So one thing that you can use as a protecting group is a trimethylsilyl ether. So it's a silica compound with 3 methyl groups. This is a trimethylsilyl or a TMS group. So that's the same thing as BR OTMS. So the oxygen is the oxygen here. This whole group is the TMS part. So once we put the TMS group on here, the reagents cannot see that this is an alcohol because there's no OH, and so it will treat it as there's no alcohol there. In order to put one on, you have your alcohol, you add TMS chloride, which is the TMS group plus a chlorine, so we've put a leaving group on here, and you use triethylamine, which looks like this. And this is just a weak base to take that hydrogen off. And then it's TMS. Plus you form the triethylamine salt. Once you have the TMS silyl group on there, you would use tetrabutyl ammonium fluoride or TBAF to remove the protecting group. So PG is protecting group. So if you're doing this reaction, you add TMS chloride with triethylamine. This also can be abbreviated TEA. So triethylamine, that will protect your group. You can add your magnesium, which will make the Grignard. And then that will react with your ketone that you want to add, followed by water. And this is the R group from the ketone, and there's your alcohol. The TMS group is still on here, and you use TBAF, and that will remove the group. And you should get the alcohol back. Fluoride has an affinity for silica, which is why it removes the group. So here are a couple of synthesis problems for you to practice using Grignard reactions and or protecting groups. So if I look at this first problem, the only thing that I see is different here is going from the aldehyde to the carboxylic acid, which currently I do not believe you know how to do yet. So we'll cross this problem out. But if we look at this one, we're having an alcohol with a bromine. And we see that we're adding carbons here and we're getting the tertiary alcohol. So because this is an alcohol chapter and we just discussed Grignards, we're probably going to need to use the Grignard in order to do this reaction. We don't want to make the Grignard directly because if you remember, Grignards react with alcohols if it's within its own molecule. So we want to make sure that we protect that alcohol first. So I'm just going to start here with TMS chloride with triethylamine. And that will protect my alcohol. Then I can make the Grignard. We have the Grignard, and if I look at what's getting added here, there's 2 carbons, this would be the undercover ketone, so really it's just acetone. I'm going to follow that with water. And when that Grignard reacts with that, I get the addition of those 2 carbons here, or 3 carbons. 1, 2, 3, 1, 2, 3, and then the OH, which is my target molecule. In order to prepare phenols, benzene is often used. You start with benzene, you add an alkene to get cumene, that gets oxidized to make cumene hydroperoxide, and then acid is added to remove, then acid is added and you get phenol and acetone as a useful byproduct. So acetone, as you're aware, is what we use in the lab to clean. It's kind of an industrial solvent. Phenol is a precursor for many chemical synthesis, including pharmaceuticals, polymers, adhesives, and food preservatives. That's really the extent of what you need to know about synthesizing phenols. We may see more of those in later chapters. Once we have made an alcohol, we can do different reactions with them. One of them is a substitution reaction. And this is one that we've seen when we did substitution reactions with SN1 reactions. If you had an OH group in the presence of acid, that gets protonated to give you the tertiary, or to give you this oxonium atom. The water would then leave as a leaving group. We can get a nucleophilic attack of the bromine to the carbocation and get your tertiary alkyl halide here. If you had a primary alcohol, that can get protonated with HBr. You can get a Br- to do an SN2 attack to give you the primary alkyl halide. If you have an alcohol and we add zinc chloride, that is going to do a nucleophilic attack on zinc. So zinc becomes negative, oxygen is positive. This whole thing now becomes a really good leaving group. There's usually Cl- floating around with the zinc chloride. We can do an SN2 reaction, and this will attack here, and this whole thing leaves as the leaving group. And that there is the electrophile. So you've replaced the OH with a Cl. So this is kind of like putting the tosyl group on here. Before we knew that OH was a bad leaving group, we would tosylate it. We would tosylate it and make it into a better leaving group, and then do whatever reaction we wanted. Inverting the stereochemistry, but this is a 2-step reaction. This one here is a 1-step reaction. And because this is an SN2 group, this also inverts stereochemistry. So zinc chloride with an alcohol will give you the chloride. It makes the OH a better leaving group, and you also invert the stereochemistry in the process. That's not shown here because the OH doesn't have stereochemistry, but if it were a secondary alcohol, you would invert that. Another reagent that we can use to do a substitution to do the same thing is SOCl2, or thionyl chloride. This OH then will attack the sulfur, and the electrons get kicked up to here. So that's a nucleophilic hug. So in this case, those electrons have gone up to here. This oxygen wants to reform that double bond with sulfur, so it'll do so, and it will kick off a chlorine subsequently. And then you have pyridine floating around, which is a weak base. This will grab that hydrogen. Those electrons go on to here so that it's not positive anymore. So that is now what we have here. And as before with the zinc, this is now an excellent leaving group. So the Cl- that was kicked off in this step can attack this carbon. This chlorine is going to attack this good electrophile here with this excellent leaving group. These electrons will come over here actually and form a double bond with sulfur. Sulfur doesn't want to have that many things on it, so it's going to kick this chlorine off. So we have the chlorine plus SO2. plus Cl minus. Zinc chloride can be used to convert the alcohol. We can use thionyl chloride to convert it to an alkyl chloride. If we want to have a bromide in place instead of the alkyl chloride, we can use PBr3. And you can see the beginning of the mechanism here. Oxygen is going to attack phosphorus. It kicks off a bromine. This is positively charged. So this Br, we have this, again, excellent leaving group. The Br can come in and attack this electrophile and kick that off. So again, these are all SN2 reactions in the last step, which would result in an inversion of stereochemistry if there was stereochemistry present. Okay, so for this practice problem, you want to look at what reagents you can put in place to get to the reactions. Here, we're going from an alcohol to the tosyl chloride. Stereochemistry is the same. This is just TsCl with pyridine. To go from the OTS to an inverted OH and do an SN2 reaction, here you can just do NaOH. In this reaction here, you are using an OH, and you have a Cl in place. We're inverting the stereochemistry, so you can use SOCl2. Option B would be zinc chloride. So either of those will give you the chloride in place and also invert the stereochemistry. We've seen elimination reactions with alcohols, and this is just an E1 reaction with the tertiary alcohol to give us the alkene. We have an alcohol with concentrated acid and heat, which would give us two products here, this being the major one with more substituted groups. We can also do an elimination with an alcohol, converting it to the tosylate. We can get an alkene from an alcohol by making it a better leaving group and then doing an E2 reaction. Other reactions that we can do include oxidation. Oxidation, if you recall, is the loss of hydrogen. So we go from an alcohol to a carbonyl. And the opposite of that is reduction, which we saw at the beginning of this chapter. If you have a primary alcohol and you do an oxidation reaction, you're going to lose one pair of these hydrogens and replace it with a double bond. So oxidation is loss of hydrogen. It can also be, if you recall, gain of oxygen. So loss of hydrogen and or gain of oxygen. If we're going to gain an oxygen here, that gets inserted between the carbonyl and the hydrogen. So primary alcohol first goes to the aldehyde and then to the carboxylic acid. A secondary alcohol will remove this pair of hydrogen. This is a ketone. There is no further oxidation because there's no more hydrogens available. So in the aldehyde here, there is still this H that could be replaced with the O. Because there's no hydrogens here, that is the farthest it will go. If you have a tertiary alcohol, there's no reaction. No H's. So tertiary alcohols do not get oxidized. One reagent that can be used in an oxidation reaction of alcohols is chromic acid, which can be made from chromium trioxide with acid and acetone, or sodium dichromate in acid. So both of those effectively will give you chromic acid. In the first step, if you have an alcohol with chromic acid, this is a fast and reversible step. So the alcohol is going to attack here, and in the process, this water is lost. And then everything that was on the alcohol will come along. This is a chromate ester. So this new bond was created there. So I'm just going to redraw this chromate ester. So the water that is present can grab this hydrogen and do an elimination. So this forms a double bond here, and that gets broken there. There's an E2. We get that plus acid. That was created here, and then the HCrO3- from there. So the primary alcohol gets oxidized to the aldehyde, which gets further oxidized to the carboxylic acid because there's a presence of the hydrogen here. If you wanted to stop at the aldehyde, which you can't do with the chromic acid, you would use a different reagent. So pyridine with chromic acid in the presence of acid create a compound called PCC. So this is a pyridinium, and this is chlorochromate, or PCC. This stops at the aldehyde. So again, if you used chromic acid, that goes to carboxylic acid. If you just want to go here, this would just be PCC. Another reagent that will give you just the aldehyde from an alcohol, so this could be H as well, is the Swern oxidation. That's their name reaction. This is the Swern oxidation. So you get the ketone or an aldehyde depending on whatever you started with. So this one uses DMSO, which is similar to acetone, except instead of a carbon, there's a sulfur there. And that will react with oxalochloride, which is this, or this COCl2. So when you see DMSO, it is in resonance. It is in resonance with this, which makes this nucleophilic. So this nucleophilic oxygen can attack this electrophile. Those go up there. So I've created an O-. These electrons can come back down here and kick this off. So there's a double bond that formed there with the carbonyl. So the Cl that got kicked off can attack this positive sulfur. These electrons from the oxygen go up onto here. which attacks here, and then that chlorine gets kicked off. So the active part of the dichloro of the oxalochloride Swern reagent is this S, CH3 plus, and the Cl. We also in the process kicked off Cl minus plus carbon monoxide plus carbon dioxide. So this is the CO2 right here. This is the CO, and then that's the chlorine. This is chlorodimethyl So if you had whatever alcohol, this can now do a nucleophilic attack on the sulfur, kick off the chlorine. And the trimethylamine that's around can grab this hydrogen give the electrons back there. That trimethylamine again can grab this hydrogen and kick that off. This is our leaving group. So in case you are, let's see, so the product that is made is the ketone. And in case you're having a minor heart attack right now, you do not need to memorize this mechanism. So both PCC, which we saw in the last slide, and this Swern reagent will give you, can oxidize the alcohol to a ketone if you have a secondary alcohol, or a primary alcohol if you had an aldehyde. If you had a primary alcohol, it will get you to the aldehyde. So primary alcohol with PCC gives you the aldehyde. If you have a secondary alcohol, or in secondary alcohol, and you use the chromium reagent, which is also the Jones reagent, or you use PCC, those will both get you the ketone. So either method will work here. This is more mild.